So this last section in Unit 5 is its own packet. It's something we recently added to Unit 5, and it has to do with solving some story problems. Now, our focus is going to be on what we call work problems, but there's going to be some other chart problems in this section, so some mixture problems and some distance, rate, and time problems. So the idea with work problems is you're going to have two people working together on the same job, and because there's two people working, you're going to get it done a lot quicker than if they were working alone. And the idea is when you have the part of a job completed by person one plus the part of the job completed by the other person, you're going to complete exactly one job. And that's how we're going to set up the equation. So part from the first person plus part from the second person is one job. The other thing you need to know about these problems is when you go to calculate what part of the job someone has completed, you might want to jot this down. A part is calculated by the person's rate multiplied by how much time they are going to be working at that rate. So when I look at this job, Amanda can clean the attic in 10 hours, and Kristen can clean the attic in 9 hours. For Amanda, her rate is that she can complete the one job in 10 hours. That's Amanda's rate. So I'm going to kind of jot that down over here. And then Kristen's rate is she can complete that same job, one job, in 9 hours. And I have no idea how long they're going to be working together. So that part is going to have to be a variable. The time that they're working together is going to stay as a variable, t or x or whatever variable you want. So essentially what I'm setting up is Amanda's part plus Kristen's part is going to be one job completed at the end of this problem. So for Amanda, if her rate is 1/10, meaning one job in 10 hours, and I multiply it by how much time she's going to work with Kristen, I have no idea what that is, I'm going to call it t. Okay, same thing with Kristen, 1/9 hours is her rate, times how much time, I don't know. But I know they're going to work the same amount of time, and it's going to complete one job. So essentially what we have here is a rational equation. t/10 plus t/9 equals 1. And we discovered through the last section that when I solve rational equations, it works really smooth if I just multiply through by the LCM of the denominator. So I'm going to multiply through by a 90. And that's going to give me 9t plus 10t, and then don't forget to multiply the 90 by the 1, equals 90. So 19t equals 90. And when I solve for t, I get that these ladies are going to work for 4.74 hours. I think they want us to round to the nearest hundredth. So that's my answer. The next problem is very, very similar. I don't think I'm going to set that one up for you guys. Let's move on to the next question, because I think part of your homework is going to be to finish this packet. So Mike can pour a large concrete driveway in 7 hours. So Mike's rate is he can complete the one job in 7 hours. So that's Mike's rate. And then Wilbur helped him, and it only took both of the guys 2.92 hours. Now what this number is, it's the t, it's how much time that the boys worked together. So when I go to set up my problem, and I haven't set up a chart yet for you, but if you'd like to use a chart, that's fine. I'll set one up on this problem. We've got Mike and we've got Wilbur. And when I set up the problem, it's going to be each gentleman's rate. Whoops, in the first column. And then the time, but remember it's time that they're working together. And then the part of the job that they have completed. So essentially what's happening here is we know rate times time is going to equal their part. So for Mike, his rate was a 1/7. And then the time that he was going to work with Wilbur, we already found out it took him 2.92 hours. Now that's going to be the same time for both gentlemen. I have no idea how long Wilbur's rate would have been had he done it alone, and that's actually what they want me to find. So I'm going to set that up as 1/x because the rate at which he completes the job by himself is a mystery to me. If I were to multiply 1/7 times 2.92, I get roughly 0.42. If you round a little differently, you're going to get a different answer. And then his rate times his time would be 1/x times 2.92. Well, this is 2.92 over 1 if I multiplied it here. We're just going to end up with something kind of gross like 2.92 over x, and that's what I'm going to write down. And I know from the previous problems that the way we calculate these equations is Mike's part plus Wilbur's part, when I add those working parts together, should come out to, oops. Oh goodness, one completed job. So, it's not the only way you could set up this problem, but I do see a rational equation, and if I multiplied everything by an x, I think I'd be in business to solve. So I have 0.42x. The x's will cancel in the next term, so plus 2.92, and then 1 times x. And when I subtract 0.42, excuse me, from 1x, I get 0.58x. And then dividing by 0.58, I find out that Wilbur's time is roughly 5.03 hours. So had Wilbur done that job alone, it would have taken him 5 hours. I'm going to let you finish number 4 on your own because it's very similar to number 3. So this next question has to do with a different setup. This time we have distance equals rate times time. So you might want to jot down that formula. Distance equals rate times time. So this Air Force is going to the air show and then coming back. So I'm just going to set it up as my trip to and my trip back. And the headings for this chart is just exactly what we wrote at the top. Distance equals the rate times the time. So we're going to make 3 columns. And if I start reading, the trip there took 5 hours and the trip back took 6 hours. So right there they told me the time was 5 hours to and 6 hours back. The average 270 kilometers per hour on the return trip. That was the rate of the return trip. And they want us to know the speed of the trip there. Well, they don't tell us that, and since we want to know that, I'm going to call that x. Now, for the last column, you notice there's nothing written there, and I don't want to introduce a new variable. So what I'm going to do instead is I'm going to use the clues I know, which is rate times time is equal to his distance. So rate times time for the to trip is 5 times x, or 5x. And then same thing here for the return trip, 270 times 6 is 1620. And the only thing I know is that they went the same trip, so the distance to the trip and the distance from the trip are going to be the same value. And that is the equation I'm going to set up. The distance equals the distance. So we're going to divide both sides by 5. And I find out that x is 324. And if you look up in the chart, what we just found was the rate of the going there trip. And I think that's what they wanted, find the average speed of the trip to the air show. So 324 kilometers per hour. Let's look at the next one together, at least the setup. So we've got Emily and we've got Jacob. So Emily and Jacob. And same headings, distance equals rate times time. That gives us our chart. And this time, let's read. Emily left the hardware store and traveled towards the lake. 2 hours later, Jacob left. Okay, I'm going to stop right there. What I found out, let's keep reading because I think they told us more about time. Traveling 75 miles per hour. So Jacob's rate is 75 miles per hour. And then he's going to catch up to Emily. So I don't know Emily's rate right now, and I think that's probably going to be our variable because if I read the question, they want to know what was Emily's speed. And right there, that tells you what your x should represent. So Jacob traveled for 3 hours. So Jacob's time is 3. Now read carefully. Jacob left 2 hours after Emily. So Emily must have been traveling for 2 hours plus the 3 hours that Jacob was traveling. So Emily was traveling for 5 hours. So same idea here, guys. We are going to set up the last part of the chart using some algebra. I know distance equals rate times time. So Emily's distance is her rate times her time. And Jacob's distance is his rate times his time. And they went the same distance, they just left at different times. So you're going to set up an equation that looks like this. And when you find x, you are going to know Emily's speed. I more than halfway did that problem for you. Okay, this next problem, let's set up our chart. We've got Maria, and we've got Natalie. All right, And again, it's distance, rate, and time. So distance equals rate times time. Oops, excuse my lines. They are ugly. Okay, let's read. Maria left at an average speed of 40 kilometers per hour. So that is Maria's rate. Natalie left, traveling the same direction, but her speed was 50. After traveling for 4 hours, Natalie caught up with Maria. So I know Natalie traveled for 4 hours, but I don't know anything else about Maria. So I think her time, we're just going to call it X, because they don't want to know how long the entire trip took for Maria. They just want to know how long she traveled before Natalie caught up with her. So we're going to call that X. And again, I think we're almost ready to set up the problem here. I just need you to think about the equation. The distance is the rate times the time. So I'm going to stop the problem there. I'm going to let you finish it. Just remember, since they are catching up to, well, one's catching up to the other, the distance that they traveled is going to be the same. So, next question. I'm going to let you set that one up on your own. I will set up the chart for you a little bit. We've got Leah and we've got Jasmine. And the ladies are driving or something, I don't know. Distance equals rate times time. It's going to be your setup. And I'm going to let you take it from there. Okay, the next questions are we call mixture problems. And again, you could set up a chart. I take a little bit of a different approach. I don't really care for charts because I can actually see this problem happening in a laboratory. So I take a beaker approach. I've got, let's see, we've got 30% sand that we're going to add to 4 meters cubed of 50% sand, and we're going to create a mixture that's 38%. So what's happening here is we've got two, beakers or bags or whatever that we're going to add together and create a new mixture. So we're starting with the 50% sand, and we're going to add to it 30% sand, and we're going to end up with 38% sand. I'm going to keep reading because they tell me something about amounts. We know we have 4 cubic meters of this 50% mixture, and I don't know how much of this I'm going to add. In fact, that's the question they asked me, so he's my X. And then in this giant beaker, 4 plus how much I added to him is how much is going to be in the new beaker or bag or bucket. So his quantity is X plus 4. Now if I think about setting that up as an equation, 50% times 4 cubic meters would be 50% times 4 written as a decimal. 50% written as a decimal, and then 30% times x would be 30% x, and then be careful on this last part. It's 38% of the quantity x plus 4, so we're going to have to distribute that. So I'm going to go ahead and just clean this up a bit. I get 2 plus 0.3x equals, let's see, 0.38x plus 1.52. And of course I'm going to solve the equation. I'm going to possibly, let's say, subtract 0.3 over and get 0.08x. And I would subtract 1.52. And I always use calculators when I do these decimal works because I consistently mess this up. So one misplaced decimal and you're going to get the wrong answer, so be careful. Turns out x equals 6. Now that's not a real clever way to answer the question. I would like you to label it 6 cubic meters of, remember in the chart, or in the beaker, that was the 30% sand solution. Okay. The next question, again, you can do a chart if you want, but I like to set up beakers because I can see it happening. It makes a lot of sense to me when I set it up this way. We've got 45% juice must be mixed with 55% juice to get a 51% juice. So any order, as long as your result is the 51%. So read carefully, it's 9 gallons of the 55%. So that is 9 gallons of this, a mystery amount of that. And then in my final juice bucket, I'm going to have x plus 9 gallons, whatever that comes out to. So we're setting up 0.45x plus 0.55 times the 9 gallons equals 0.51 times the x plus 9 gallons. So you are going to go ahead and solve that equation. I have full faith that you can do it. And 11 is really the same. They don't give you percentages this time, but it's the same idea. It's dollars per ounce of coffee, I think, is this problem? Yeah. So we've got $22 per ounce must be added to this cheaper coffee, $14 per ounce, to create a mixture that's $20 per ounce. So I believe they said we don't know how much $22 per ounce coffee should be added, but the cheap stuff, we know we have 3 ounces. And in the combined coffee, it's going to be x plus 3. So this one doesn't have decimals, which makes me kind of happy. I'm just going to calculate this, and of course I'm going to be using my calculator, just because I don't want to make silly mistakes. I'm going to let you finish that problem. I'm going to let you set up number 12 completely by yourself. And then the rest of the problems here, I think, are going to be part of your homework assignment. So these first 2 are work problems, so I just want you to remember that the part from the first person plus the part from the second person is going to equal 1 job completed. These 2 questions are contingent on you knowing distance equals rate times time, so you might want to set up a chart and refer back to a previous problem. And then these 2 problems are mixtures, so beaker problems, if you want to call them that, but they are mixtures. So be careful here when you're adding pure water and we're talking about acid solution. Pure water is 0%, so you're going to have a 0 in your beaker in your chart in that case. Okay, that is your introduction to work problems. When you see me in college algebra next year, you're going to have a ton of those.